Hello, everyone. It's a pleasure for me to introduce Pau Amaro Seoane. Professor Pau Amaro Seoane is profesor titular at the University Politécnica de Valencia, and since 22. He did his PhD in Heidelberg after studying theoretical physics in Valencia. And he worked on stellar dynamics and supermassive stars, but got interested in gravitational waves during his PhD. Apparently, people were telling him, "What are you doing? There's no data for this. This is just theory. Maybe it's a fluke. It's nothing real." And he bravely went for this. And funny anecdote is that he got a Canarian fellowship in collaboration with Germany to work at the Albert Einstein Institute. And with that fellowship, apparently people were also very surprised there. What is an astrophysicist doing here? This is very theoretical institute. And then after a while, they really got interested in this interaction between theory and astrophysics, a very theoretical, relativistic theory and astrophysics. And he got, they created actually a group for him so that he could lead that group for 12 years at the Albert Einstein Institute, becoming a renowned expert in gravitational waves as well. And since then, he has been collaborating with many people, among them with Reinhard Genzel, the Nobel Prize in Munich, where he has also, he's part of the theoretical team. And he was Ramón y Cajal. He actually was interested in coming here to the IEC, and hopefully we can count on him soon. So please go ahead and give us a talk on chartography of spacetime around supermassive black holes.
So I need this for people who are connected, right? Okay, so I have been told that this should be very general, broad, and without going into details, and this is what I have prepared. I have a lot of slides. I don't intend to go through all of them. I just want to make sure that what we see, right? So first of all, a few words. High energy phenomena. So this is, I don't know how many people here working on high energy astrophysics, but this is like a little provocation for you. So high energy phenomena. So this is when Kip was giving this press conference after the first detection of a gravitational wave in 2016. Think about the following. The first, well, unfortunately, this is covering the thing, but this is the power output of a weak source of gravitational waves, okay? So the first, don't look at the screen because we can go back like this. The most interesting thing about the first detection is that it was the coalescence of two black holes of masses about 40 and 40 at a distance of about, I think, 480 megaparsecs. And that signal has been traveling at the speed of light, principle, to get us on Earth. And the time that it has been traveling is such that that merger happened when life here on Earth was starting at a cellular level, okay? Then we had to wait for the dinosaurs and many more millions of years, and that thing was still traveling until it got to Earth on September 2015. Now, that's a very long distance, right? 480 megaparsecs, but nevertheless, in gravitational wave astrophysics, this is, so to say, around the corner. When you think about the total output, power output emission of that thing, is so that source emitted 50 times all of the power output of all the stars in the whole universe put together. So put all of the stars in the universe, take their power output, multiply it by 50, and that thing was even higher. Of course, here I am cheating a little bit because I'm talking about power output, right? So you have to divide by time. This was like 20 milliseconds. So to divide whatever by a very small number, you get a huge number. But still, if you look only at the released energy, that corresponded, that source, GW150914, corresponded to putting 3 suns and converting them into energy, all of that mass into pure energy. And these are the weak sources. And by the way, when you go and translate this into other units, this corresponds to about 10 to the 54 ergs, which is 5,000 FOEs. Don't know whether you know this unit, but this is 51 ergs, FOE. It's very fun. It's like about 5,000 supernovae. And the total energy of 2 supermassive black holes of masses 10 to the 8, not of 40 and 40, corresponds to releasing 5 millions of suns into energy. So this is a big perturbation, right? And that corresponds to 10 to the 60 tera electron volts. So this is high energy. Okay? Now, what do we know about black holes? Well, we know a couple of things. One of them is that general relativity predicts them. We know that. And we have the singularity theorem, a lot of theory about trapped surfaces. From the point of view of physics, we have a long list of indirect observational indications that these things should exist, right? We have even a longer list of theoretical motivation to believe that they should exist. And as usual, this is actually a usual situation, not only in physics, but in any branch of science. So why do you need such long lists? The answer is because you don't have one evidence, right? So if you had one evidence, you would be fine, and you would not need very long lists. So we don't have a direct evidence, right? Or not? Well, there is this thing here. Probably you know about this picture. It's the first detection of this gravitational wave. This is the strain, which is something like the amplitude, if you want. It's how much you can stretch or compress your interferometer. So the arm length of your interferometer divided by the length of that interferometer. In the case of LIGO, we're talking about kilometers. So you can measure parts in 10 to the minus 21 in those few kilometers. Okay? It is so sensitive that you have to take into account the noise, the quantum noise that is happening on the mirrors. And okay, so you look at these things and you say, okay, well, this is the theory, that's the data, and this is the first part of the evolution, which is kind of sinusoidal, so to say, is what we call the inspiral. Here we have the merger, and here we have the ring down. But the fun thing about this is the following. When you see this, actually, I have been told, I am not in the LIGO collaboration, but I have been told that when they look at this, they say, well, this corresponds to Nobel Prizes, right? One Nobel Prize for the detection of gravitational waves, another Nobel Prize for the detection for the, but no, I don't like the word proof because this is not mathematics, but for a very strong evidence that black holes exist. And that's wrong. That's wrong. Because in order to show that these things are black holes and nothing else, you have to get to this part of the evolution, and you have to get there with a very high signal-to-noise ratio of hundreds. And you don't have that. You have at most, and this was one of the loudest sources, you have at most 25 in the whole evolution of the thing. So no, this is not a proof or a very strong evidence that black holes exist. And as a matter of fact, quite a few people, smart people like Vitor Cardoso and collaborators, he explained exactly the same signal with the collision, if you want, I don't know how to call it, or fusion, I don't know how to call it, coalescence of two wormholes. So he managed to replicate the data with two wormholes. Another interesting paper is this one by Cecilia Chirenti, a friend of mine, with Luciano Rezzolla. They managed to reconstruct the same data with two gravastars, which are extremely strange objects. I don't know whether you have heard about them, but they have a surface. That's the most important thing. And it looks like we are not quite there yet. Well, so we know that these things are gravitational waves, but from the point of view of being completely certain that these things are general relativity black holes and nothing else, we're not there yet. We need to move on, right? So by the way, it is so Vitor and collaborators and Cecilia, etc. It's not that they are crackpots, that they don't believe that black holes exist. But the point is that you have to show that this thing can only be fitted with a black hole and nothing else, right? That's the point. Okay, so it was an exercise. Now, oh yes, this is a little bit of propaganda. I'm apologies for that. But a year before the first observation, I published this paper with a postdoc of mine. He's now a professor at Peking University. And we predicted that black holes, as measured by LIGO and Virgo, should have masses, larger than the nominal 10 solar masses, between about 30 and maybe about 100 to 100. They should have low spin, and they should be circular. Okay. This is what it looks like nowadays. This is the whole family of mergers that LIGO has and LIGO and Virgo have detected so far. This is the mass. So this is the 20 I was talking about and beyond. So all of these sources, all of them fit in our prediction. And actually, the paper that published about the Nobel Prize, they cite us, which is something that made me very happy. Anyway, enough of propaganda. So why is this important? So this is important from the point of view of fundamental physics. If you want to be politically correct, you have to say, look, this LIGO and Virgo detections of mergers and the inspiral, because we're talking about inspiral, but we cannot see the collision of neutron stars, are a prediction of general relativity in the strong regime, which is a very long way of saying, general relativity is correct. Also, we have, forget about proof, we have a very strong evidence that gravitational waves exist and that objects consistent with the general relativity black holes are present in the universe. Because proof is a mathematical thing. And this is not a proof. But it's a very strong evidence, Okay. In any case, if you want to loosen up a little bit, you just say gravitational waves exist and it looks like a black hole should exist as well, okay? So from the point of view of astrophysics, it looks a little bit more modest, but it is not. We show that these dark objects, which I am going to call black holes from now, okay, exist, and they have masses larger than the nominal 10 solar masses, because I personally don't understand how to form a black hole with a mass larger than 10 via, standard orthodox, if you want, a cell evolution. But I'm not an expert on cell evolution. Anyway, they form binaries and they merge. Okay. Now, so we have found out that we don't know much, not to say nothing, about black holes, supermassive black holes. So what about supermassive black holes? Do they exist? Well, by extension, you should say, well, if we don't know much about the supermassive black holes, what about supermassive black holes? Do we really know that huge, massive thing, for instance, at the center of our galaxy is a black hole, nothing else? Well, let's look into that. We have, of course, this image. This is a very pretty, impressive image. By the way, this is coming from a comic called XKCD. Here you have, usually they say this is not to scale, right? When they show these pictures, in this case, it is to scale. It is to scale. So at the center of this thing, you have the sun. This is the orbit of Pluto. And this is Voyager 1. This is the farthest away that humanity has managed to go. And it looks like there is something dark surrounded by a cloud or a torus, or you can call it a disk if you want, which is emitting radiation, right? Okay, this is very beautiful, but if you ask me, the most robust evidence that there are very massive things at the center of galaxies is in our Milky Way, in our own Milky Way. So all of you know that probably, but when you look at the galactic center, there is something strange happening. I always ask the students, but are the students here? Yes, I see one there. So I want to be asking questions to you all the time. So no, but I like to ask questions because otherwise it gets boring. I go on talking for 45 minutes, and in the end you hate me, and everybody's sleeping. So, but I can ask back if you want. So, no, but you're not a student anymore. So anyway, so what doesn't do a star in the sky on a human time scale? So you go to the beach, it's holidays. You look at the sky, you say, look at Orion. This is so romantic, so beautiful. You go next year, it's the same thing. You go 10 years later, Orion is still there. You go on, you retire, Orion is there. You die, Orion is there. So stars don't move. Stars don't move, right? But when you look at the galactic center, there is something strange going on because the stars are moving and they shouldn't. We know the stars don't move, they move. And they're moving on very short time scales of months. It's like you see the corner of Orion here, and 1 month later is there. So what happened? And so they have been taking the telescopes, pointing to the galactic center, poof, taking a picture, waiting a couple of months, pointing to the galactic center, poof, taking a picture. They have been doing that for over 20 years. Why? Because they feel bored? No, it's because there's a bunch of stars, about 100 of stars, which are, by the way, very young, and we don't understand how they got there. And they are revolving around one point. And that point is a very strong radio source called Sagittarius A star. And when you fit the the orbits with a very small, mild relativistic corrections, it turns out that in order for those orbits to be there, where we see them, there should be a point mass with, well, a mass of about 4 million solar masses within a radius of 22, I think, million kilometers, which is about 1/3 the distance between Earth and the Sun, which seems huge, but you being an astrophysicist, because I give this talk a lot of times to people working on general relativity, I say, it's a very, large distance, but we know that it's a very small distance, right? So it's actually, by the way, impressive that such a small thing, a supermassive black hole, has such an impact on the whole galaxy, because it's like a virus from the point of view of the galaxy. Anyway, so yeah, we see that, and that's impressive. But that's the best you can do with light. And this this got the Nobel Prize to these people working on this, and also was shared with 3 people, Andrea Getz in the US, Reinhard Genzel, and Roger Penrose. But it is extremely difficult to work looking at the galactic center because you know that we're on the disk of the galaxy and we're looking at the center. So we have all of the stars in front of us, all of the dust, all of the gas. We have a lot of obscuration, and these people have managed to do what in principle is impossible. But anyway, it's very impressive. So I'm trying to motivate. So this is the best you can do with light. And we're used to light. We like light, right? Because we have eyes. We have evolved to like light. But light is difficult and it's problematic. And I'm going to explain to you why gravitational waves makes everything easier, and also why we are interested. This is not just because we're interested in, showing that general relativity works very well. There are other things that we want to look into. It turns out that what we look outside and what is inside of the black hole is connected. So if the event horizon is rotating, that will lead to a kind of singularity. And if it's not rotating, you will be talking about a different singularity. Well, anyway, a singularity, you see these pictures on the internet, right? This is the Big Bang, and they draw a point, and from there, the universe is expanding. Well, first of all, that point is, if it's the origin of space and time, is embedded where? So, the paper is also a space and time. What does it mean? Anyway, a singularity is not a point in space-time where gravity becomes infinity. It's something more complex. You must have a variety, actually a mathematical variety, which cannot be embedded as an open set of a strictly larger space-time with a causal curve which has a finite past or a future or both. Okay, so it means that in our universe, you are born here, you evolve a little bit, and you die there. Okay. Now, the interpretation is not very clear. So when people ask what happened before the Big Bang, I don't know. I mean, general relativity is very honest. It's a very honest theory, and it tells you, I work everywhere, but here, I don't work. At least it's very honest. And this, I usually tell to the students, it's like when I tell you, we have, sorry, but you're the only student, so I'm going to tell you. There are more? Okay, then let's go to the, so what's your name? Pedro. No, it's fine. I have, oh, nice. Well, so if I have 0 candies and I have 0 children, how many candies do I have to give to every child? The answer is, right? So that's a singularity. When you say, that's a singularity. It has a very fancy name, but it's a very clear concept. This is something that our brains are not made to understand. But in any case, what is clear in physics is that a theory has always replaced a previous theory. A general relativity is wonderful, but at some point it will have to be replaced, right? So we don't understand what happens beyond that, but that's fine. But we have to get there. We have to get information about that singularity in some way, because it is where our best theory of gravity is breaking down. So we have to manage to try to get some kind of information. We cannot, of course, get into the black hole, but we can try to get as close as possible to the black hole, right? So it turns out that the event horizon at the type of singularity that you have are connected. They prove that as a rigorous mathematical theorem that I'm not going to describe today. Anyway, if you have information about what's outside, if you have information about the rotation of the black hole, you have information in principle of what is inside. And anyway, I'm going to skip this. And another interesting thing that is going to be much harder, sorry, but I like to walk up and down, is that it turns out that, well, you know that the integral over the curvature of a manifold is 2 pi the Euler characteristic, right? This is why a triangle, the sum of the angles of a triangle is 180 degrees. So via the Gauss-Bonnet theorem, you can connect geometry and topology. Why is that important? That's important because, well, in principle, the topology of a black hole is a sphere. This is what they say, but we don't know. We don't really know what is a topology. If you have information about the geometry, what is the transition of that into topology around the supermassive black hole? And that's important. I'm not going to talk about this now, but it gives you information about the structure of a space-time. And in principle, you could extend that to large structure things, right? But I don't want to mention that now. Anyway, but there is something. I am cheating. I am not telling you the truth, because the Gauss-Bonnet theorem works for 2 dimensions, and here we need 3. And it is easy to extend it to 4, 6, 8, but it's very difficult to extend it to 3. Anyway, but in any case, so now, stream masters and inspirals. Look, if you need, so you want a source of gravitational radiation, and I'm going to just summarize very quickly. You need a quadrupole, and that means that you need a deviation of spherical symmetry. And in nature, in our universe, students, in particular you, sorry, I'm going to disappear tomorrow, don't worry. what is the most common thing in the universe which does not have spherical symmetry when we talk about the stars? A binary, right? Out of all of the stars that are in our universe and our galaxy, about 50% of them are in a binary. So that's a wonderful way of producing gravitational waves. And by the way, when I go like this, I am already emitting gravitational radiation. So you need that. Okay, but you need that at a very large speed and with very high masses. What kind of binary has very large masses in a very small volume, so with a very high compactness, and moving at very large velocities? Black holes, binaries of black holes. And in particular, there is one particular source, which is my favorite source, because it's about, you have a supermassive black hole with a small compact object. You know what happens when you take a star, like a extended star, like our sun, and you throw it to the supermassive black hole? It will be stretched, deformed because of tidal stresses, tidal forces acting onto it. And if it gets close enough, in principle, boom, right? It's a tidal disruption. So if you do the same thing, but with a compact object, like a neutron star, or a stellar mass black hole, or a white dwarf, that doesn't happen. First of all, because it's much smaller, and it is very, very dense, right? So that thing, if Paco is a supermassive black hole, right, and you have a star coming from far away, it will, revolve around him. Nothing will happen, but there will be dissipation of energy. And that dissipation of energy follows the equation of a wave, which is why we call them gravitational waves, right? This thing goes to apocenter, comes back to the supermassive black hole. What is your mass? Comes back to apocenter, but it's losing energy. So the semi-major axis is going to what? Right? It's going to be reduced. It's going to be shrinking. But then we also have relativistic effects. You know that we have precession of the orbit. You have heard about the precession of Mercury. What you probably don't know, or many people don't know, is that 98% of the precession of Mercury is Newtonian. And only 1.8 or something like that is relativistic. This was the big success of special relativity. So you have precession. So you go revolving around Paco, you shrink the orbit, you move around this, you precess. But if he was spinning, you would have frame dragging effects, which means that space-time around him is going to be tilted with respect to me. So if I am coming from far away, and the space-time here is tilted, I initially go on this orbit, and then I go up. So the inclination changes. So in the end, you have this small object basically exploring all of phase space around the supermassive black hole, right? And how many cycles before this small thing plunges onto the supermassive thing? Well, it's roughly speaking the mass ratio. If this small thing has a mass of 10 and Paco has a mass of 10 to the 6, how many cycles? 100,000. So this thing is going to revolve around Paco 100,000 times before it disappears. And every cycle is, you have to think of this like it's like a camera taking pictures of a space-time. You have all the time a very strong emission of gravitational radiation, but in particular, pericenter, you have a very strong burst. But you're going to have a burst here, 100,000 of them. And you can actually mathematically prove that this thing is going to fill up all of the space-time, all of phase space, and so that by the end of the process, you have a collection of 100,000 pictures of a space-time, of warped space-time in the strong regime. And then you can start doing, interesting things. You can get or extract information about the geometry. In principle, you can make a connection with topology. In some sense, it's like when people before took a ship and they went to a new territory for them. Probably other people were living there, but who cares, right? And they were drawing the coast because they wanted a map. They wanted to understand how does look like that thing, that new thing. How does it look like? So we want to understand what is geometry here. We think we know, but what if there is a surprise? And what is the connection with topology? So this is what you call an extreme mass ratio in spiral. Because it is extreme, we're talking about 10 to the 6 or a million solar masses, and a small object with a mass of 1 or 10 so it's an extreme mass ratio, and it's an spiral because it's in spiraling. It's getting closer and closer and closer and closer and closer, right? Okay. Now, with Lisa, in principle, we have heard about Lisa. And by the way, if we have time, and I don't know whether we have time, I will show you a very nice and Hollywood-like movie about Lisa. So maybe somebody can ask me during the questions, can you show the movie? I will show the movie, okay? So I'm going to show you now a video, but there is something, yes, a video which is very nice and very interesting. So I have to stop sharing, I guess. And I have to share a different thing. Wait 1 second. Let's go like this. Yes. And like this. Like this. Yeah. Okay. So, don't forget the website. I have to share it, of course. If I don't. Thanks. So, like this, because always microphone. Okay, now. So a very important thing. Look at first of all, look at this thing here on the bottom. This is one of the polarizations of the gravitational wave. In this case, it's the plus polarization because gravitational waves have they have two polarizations like light, right? But the interesting thing about this is the following. Look at these small peaks, these small bursts here. This is every time that this small black hole is getting extremely close to the supermassive black hole. The mass of the supermassive black hole is of 3 million solar masses, and this small black hole is a stellar mass black hole. Here you have how many days before the small black hole crosses the event horizon, and the relative velocity, which is 20% the speed of light. Okay? Now, one important thing that I want to mention is that it took us, and us is in quotation marks because I didn't do anything. That's true. But I like to share the glory of other people. It took us like decades to model one of these peaks. Like, I'm not exaggerating, like 30 years. Because you have to solve general relativity, the two-body problem. You know that the two-body problem has not an analytical solution, general relativity. And the interesting thing is that there were competing groups in both Europe, in particular Germany, the US, but also Japan, etc., trying to develop codes which would integrate Einstein's field equations in the strong regime for two bodies. And all of them were failing miserably in a horrible way. At first, they could not even integrate one black hole. It was blown up. Then they could have managed to integrate one black hole, then two black holes, a quarter of an orbit, it would explode. And they were, pumping millions and millions of euros into this, and nobody managed. Until one guy in in a very, I saw that office, by the way, in Caltech, a guy in a very small and dark office without windows, I think, he came up with an idea. And he came up with an idea, which is basically, well, it's not a trick, but I don't have time to explain it, but it's a very nice idea. And he thought, oh, well, maybe there's this transformation. And yes, the transformation worked. He wrote his own code on his laptop, and he proved that he could solve it. Nobody believed him. And he was applying for jobs, and people were laughing at him. What do you mean you have solved it? Come on. We're spending millions of years of years here. Come on, show off, show off. But then somebody said, well, what if the nice thing is that there were these competing groups because they wanted to be the first one, right? And they adopted that transformation with their very different codes, and suddenly all of them were working. And all of them were given the same result. This was in 2005. This is why people call it the golden year of numerical relativity. And this guy has now a professorship in Princeton. His name is Franz Pretorius. And he's extremely nice. So it took us, again, decades to solve this thing. For black holes with similar masses, like a 1, so mass ratio of 1, 5, at most 10, because the higher the mass ratio, the less and less linear these equations become, and they are a nightmare to solve. And we're talking here about mass ratios of 1 million. So right now, we don't know how to solve this problem. Okay? So this friend of mine, Steve Drasko, was a very fun guy. He was working with me at the Max Planck, and I have a very fun anecdote. We found that one day we were for a walk, and very close to the Albert Einstein Institute, we found a huge field of marijuana. But it was all male plants, so they were used, for fabrics, for clothes, etc. But it was a very fun day. In any case, he has made this movie. He has solved the equations, and he has enhanced the frequency so that you can hear it. So it's audible. You can hear it, and you're going to hear that it's going to be increasing higher. It's going to get higher and higher over time. Wait 1 second. Okay, let's move. Let's move a little bit forward. I have to get far away. 500 days before the merger, right? And the current average speed is, I'm sorry for, I don't have a solution for this. The current average speed is 24% the speed of light. Look at the evolution of the waveform. It's becoming more complex, right? It was just one thing, you have a big sky. You will also hear the frequency increasing. It would go like that. You can have a question for the student. And if you want to put something. Okay, so pay attention now. $500 days, 24% of the speed of light. Now, something interesting. Here, contrary to the data problem, we have 3 fundamental frequencies. Whenever these frequencies. Okay, yes, let's get the rest. But they hear me, I think. I don't know the people at home. Can you hear me? Okay, I'm going to speak louder now. This is going to show the result of that. So the frequency increases, and you get a more and more structured here. And the problem is that you have to mask that. You have to mask that. You have to mask that with a very small error. Because if you're off the phase, you're going to miss the error somewhere. But we're not by the way, one of these small bits is what LIGO and Virgo are detected. And it is a very complex thing, and it lasts for about a millisecond. So this source is emitting gravitational radiation for months, if not years, from an atmospheric source, or one source. Okay. So, okay. You also will have the impression that this one moves from the right to the left. That is an optical illusion because you are actually inside following. And the frequency is going to increase more and more. Now, the question of the experiment, is what is going to happen by the end of the movie with sound? So it's going on. I want to know what's going to happen when we have a zero. So, what do you think? Quickly, because at any time, you, what do you know? It's going to go down like what? Can you make it with the voice of oh wow, just okay. Good answer. I like it. Nice job. You. It's fine. It's not enough now. People have said that if you don't know in 1 minute, it's fine. Okay. But what recommendation do you have? Who first come? Huh? Who first come to go here? But the circle you down the also. No, I'm asking. I'm not saying it. I think the frequency increases at some point where you can like notice something over the but that's just going to for a while. And then like what was it? Yeah, maybe you stop hearing at some point. Yeah, but I think that at some point it's zero. What? Zero. But how do you reach that zero? Constant. You solve it. Constant, yeah. If you solve the frequency, you can use it the constant sound and you get yes, but people don't know the way. No, ask me. That is nice, right? Because it's only solved functions. Yeah. What did you eat? So good. 3 plus, you have about oscillation, right? Yeah. Plus, and it's zero, right? Francesco again. Come on, you are changing your opinion because here. I didn't hear. Come on. Okay, do you think it's going to go with the same one to I don't know, like that? Shot. Raise. Really? Let's go to the president of Sam. Are you? But I thought you were smart. Okay, let's see. By the way, you're going to see resonances building up here. Very beautiful geometric figures, which are real. So 90 days, like 3 months before the merger, you see these nice resonances. So sharp, because we said so, most of you, right? Are you really sure? Last chance. No answer. $50 days. By the way, look at the structure of this thing. This is crazy. This is a nightmare to match. Okay, last chance. Oh, that's right. Okay. Now, the question is Why silence? Think about it, because I'm going to ask you. I have to change the thing. So why silence? Where's this? Francesco, say something. Francesco, say something. Because so what is the defining characteristic of a black hole? What is the defining characteristic of a black hole? The event horizon, right? So what Francesco is saying is that it crosses the event horizon and we cannot get any information about it, right? 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 Wait, but I remember this thing about the special relativity. If you're an external observer and there's a black hole, you take a chair, I throw the chair towards you, you're the black hole, and I see the chair getting slower, slower, and then it freezes. Actually, in Russian, they used to call black holes frozen stars. So as an external observer, I cannot see the thing crossing the event horizon. So why does it disappear? Yes, but why do we have this puff sharp? Why? Well, yes, yes, yes. You were talking. You were talking. Come on. Come on. Francesco. Francesco, something? What redshift? Come on, come on, come on. No, but it's easy. The problem is that you get extremely close. He's kind of right. You get closer and closer to the supermassive black hole, to the black hole, and the thing suffers a kind of, it is not a Doppler shift, which is huge. And it stretches the signal almost instantly. And you have the impression that there is silence. But the only problem is that you have a huge kind of redshift, okay? So, stream masters in spirals. There has not been any other mission conceived, planned, or even thought of ever that can do the kind of science that you can do with these things. These are very strong words, but they are true. Okay? General relativity is nice. We like general relativity, but it is a theory. And again, every single theory has been replaced by a better one. You could use these memories to probe the geometry, but you can also start testing what I said, general relativity, because you have a collection of 100,000 snapshots of space-time. You can reconstruct the geometry. And by the way, this is something amazing, which I like a lot. You measure the redshifted parameters, such as the mass and the spin, with a ridiculous error and without any modeling. This is a direct reading of the parameters, because with a cell phone, if I take a picture of you now with a cell phone and I send that picture to you, this is a radio wave which goes to some satellite, bounces back, gets into her cell phone, and that thing is transcribed into a picture. So this pixel is red, this pixel is blue. And in that radio wave, you have the picture, you have her password, my password. So there's a lot of information encoded in that wave, right? In these gravitational waves, you have a lot of information, and you can extract them. In particular, for instance, you can retrieve the information about the mass with an error as small as about of the supermassive black hole with an error as small as 0.1%. And the spin if you are looking at the galactic center, the numbers go crazy. You can measure the spin with an error of 10 to the minus 11.
Very extreme signals. Can you predict them? What is the limit?
Sky is the limit. I mean, yes, you can do it. No, I'm going. Okay, the mass range. That's important. Thank you for that point. The mass range for LISA is between 10 to the 7 and say 10 to the 4, with a sweet spot around 10 to the 6. Okay. And the problem is that this is a problem of 10 orders of magnitude. Going from galaxies, you know that I have this note here for people working on relativity. You know that we go from kiloparsecs. You multiply that small point here by a factor of 1,000. You get into cluster dynamics, which is still Newtonian. You don't care about general relativity here, but it is collisional in the Boltzmann-Blasov meaning. So you have exchange of energy and angular momentum. You multiply that small dot over there by a factor of 10 million, and you get into the interesting regime. So it is a hard problem. And can we detect them? Because I have been talking a lot, but I didn't say anything about detection. This is wonderful, but if you cannot detect these things, what are we doing? So don't spoil that. Yes. So the point is, it's fine. I'm joking all the time. Paco knows that. Can we detect them? And it turns out that yes, there is this thing, but I don't know whether you know how. I'm going to make I'm going to finish because I've been talking a lot. I don't know whether you know how these things work, but it is crazy. You have 3 satellites. You know that the LIGO interferometer has a length of a few kilometers, right? But we want to go to larger scales. It's like what you did with a telescope. There's this atmosphere. The atmosphere is, ruining our observations. Just take the telescope and put it outside. Easy. So here we want to construct an interferometer with an arm length of 2.5 million kilometers. Where do you put that on Earth? You cannot. So put it on the sky. But you need a precision of 1 picometer in those 2.5 million kilometers. So you have 3 satellites. Inside of the satellite, you have something which is in free fall towards Earth. And you are constantly measuring the distances between the 3 masses in free fall. But of course, the satellite cannot touch the free falling mass. It has to protect it. It has, by the way, it has to discharge it from cosmic rays without touching the masses, which is not trivial. And yeah, so what do? You go to ESA, right? This is the paper, the white paper. And you say, look, we need 1,000 million euros. Say, okay, what for this? Can you do it? So that's the problem. The problem is that LISA was always an experiment which was 10 years in the future. So in the 80s was planned to be in the 90s. In the 90s was planned to be in the 2000, 2010, and so on. But finally, in 2017, LISA received its clearance goal from ESA. It's ESA with a small contribution from NASA, okay? And yeah, so I have been always saying, so the problem with LISA is you go to ESA, say, I need 1,000 million. I say a lot of money. And I used to say, it's such a huge amount of money that it's equivalent to 2 seasons of a Spanish football league or whatever. But one day I took the time and I calculated it that it's not 2, it's half a league. And by the way, yes, only with Barca and Real Madrid you could fly LISA only, Spanish funded, etc. But anyway, so it's very expensive, very expensive. Okay, so ESA said, can you really do that? Show that you can do that. And we had a Pathfinder, as a shrunk version of LISA, which was, just a technology mission. and they launched it. I was scared to death. The best thing that could happen is that it would explode because, okay, but we don't know. But the worst thing is that it doesn't work. But fortunately, look, this is some kind of differential acceleration as a function of the frequency. And these are the requirements imposed by ESA about the LISA Pathfinder. These are the requirements for the full mission. And in blue, you have the data from what we got in 2016, a few months after launch. And a few, 8 months or something like that, they got a sensitivity of about 2 orders of magnitude larger than what ESA was requiring. This is what happens when you do something that has never been done before. So depending on rates of frequency, we did between 10 and 100 times better than the requirements. Yes. 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 Well, you say wow, but it's not that wow. So it's look, if it's like, did you know? Yeah. Well, this is look. You're getting to 2 times 10. No, sorry, 8 times. What is this? 2 times 10 to 15. And yes. So depending on where you are, well, yes. Anyway, so ESA say, oh, very, very nice. We're going to fund this. And our community, went from, a number of about 20 people that we were about this size of people here. And now the LISA collaboration is of the order of 1,100. Of course, you're talking about 1,000 million people. 1,000 million euro. People get interested and they join. Anyway, I am almost running out of time, which is a pity because in the second half, which I'm not going to talk about, I just was about to talk about a new source of gravitational radiation for LISA in our galactic center, which are brown dwarfs orbiting extremely close to the supermassive black hole. But we don't have time for that, but it's looking impressive because it is so close that the signal to noise ratio can go up to 10 to the 3 or 10 to the 4. So these things are going to be boom. Okay, so let me just skip and go to the conclusions. And look at the, okay, okay. So gravitational waves and candidate black holes. I check my list. So we have LIGO and Virgo directly detect the gravitational waves. Done. We have detected merging black holes, probably black holes. Done. We have detected in spiraling neutron stars. Done. And we have seen the kilonova associated to that source afterwards, so that you have opened up, you have seen electromagnetic counterparts. It has opened up a new field of research, which is multi-messenger astronomy and gravitational wave. We have done sub-femto G, think about that, sub-femto G measures with the LISA Pathfinder. We have now finally a firm launch slot for ESA. Sorry, for LISA at ESA. We have, well, I didn't, but we have got the Nobel Prize 2017. Kip Thorne and collaborators. We have seen, so to say, the event horizon of M87 because of the Event Horizon Telescope. We have got the 2020 Nobel Prize, okay? And but probably the most important point is the next one, because this is the thing which is really deciding everything. We have got fashion involved in gravitational waves. I saw this in Korea in 2017, and when I saw that, I said, okay, my future is bright. Now I know it. And okay, that's it. Thank you. Yes. No, I am at the library with the students.
Well, thanks a lot for the very nice talk. I wanted to ask you, in this bright future for gravitational waves, what do you foresee as major milestones and discoveries that we hopefully will see in the next, like, say, well, few years slash decades? Which are the major discoveries that you foresee we will see in the gravitational wave field in the next years or decades? Or what would you like to see as discoveries?
What I would like to see is actually this. So, we have to wait until Lisa flies to see these extreme mass resonance spirals that I was talking about, because they are, for me, the golden source of gravitational radiation. But the point is that I didn't talk about that. But in principle, with LIGO, you can already see intermediate mass resonance spirals if intermediate mass black holes exist. But I mean, if you see things with a mass of 30 or 100, and you see things with masses of 10 to the 10, it stands to reason that in between, you should have black holes with masses of 10 to the 3, 10 to the 4, and those sources should be already in the data stream of LIGO. The problem is that they don't know how to look for them, because they look like a glitch, like somebody, stepped and hit the detector. They have a boom, and they don't really know what it is. Lisa. No. When I say that, I was talking about the total mass, no mass ratios. You don't care. I mean, what you care about is the range of masses, which is between a few 10 to the 7 to, say, a few, well, being extremely optimistic, a few 10 to the 3. No, talking about the mass. Yeah, but what do you care? Do you have maybe 10 to the 6 and 4 times 10 to the 6? It's 10 to the 6. Or you have 10 to the 6 with a small black hole of mass 10. 10 to the 6 plus 10, 10 to the 6. Oh, yes, this was another question for the students. I forgot. I said that we cannot calculate this waveform, but I was showing a movie with a waveform, so I was cheating, right? So you got it. So what was I showing there? Well, I was showing something that it's called clutched waveforms, and clutch is a word in English I recently learned. I have been using that word for 15 years. No, actually 20. And I recently learned that a clutch is a synonym in English for crappy. So these are crappy waveforms, but they actually work for detection and a little bit of parameter extraction. They have been using them on synthetic data, and they seem to work. They're like a patched, horrible, not from first principles. They're like patched things ad hoc. Yes. Yes, it's just a quadruple plus some post-Newtonian corrections. But as I said, this is dirty. This is a dirty work. From first principles, in principle, you would have to work on the self-force problem, which is extremely hard for a couple of reasons that I can explain if you want. But they have been working on that for 30 years, and they go to order 2, order 2.5, and it's crazy.
Okay, thank you very much, Pau, for the very nice talk. We're going for coffee, I think, with him. If you want to ask more questions in private, feel free to join us.
I'm supposed to stay here. Where I want. It's not so bad.
Yes.
I was so full of my own affair in Puerto Santiago that I totally forgot your birthday. I'm so sorry, Armando. So sorry. I totally forgot it.
But it's perfect because you are here and.
No, it's oh my God.
Well, so next year you have to. Again.
Yeah.
Okay.
Because every time every time I go to Puerto Santiago, I with my feelings because of my mother, because my mother died there. And, yeah, and so it's always very, very.
So you can. You used to come to the they, nothing.
One. Because I didn't like very much that they spent the winter in Canary, even me and my sister in the winter room.
I think that. So. The only one. Has no value. So we have to.
You like to go to the toilet.
Yes, of course. You can go this way. The closest one. voy a buscar. Porque ese no es el contenido. A ver si yo estoy aquí. No hay más baterías aquí. No me ha parecido ver más. Voy a buscar. Hola. ¿Vienes a ayudarme?
¿Qué?
Que si vienes a ayudarme a poner este ordenador.
Pero de eso no es nada.
Nada. Como ha dicho Enaira que iba a buscar a Jorge, pero no era este Jorge. Otro Jorge. Vale, vale. Ah, vale. Hola, Jorge. Eh, So when you started this, it was supposed to have ¿te salió una pantalla? Cuando yo hice de Windows, ¿te salió una pantalla? Puede ser. Bueno, pues vamos a apagar y volverlo a encender. Espérate. Va. El ordenador no es ese, this is not the laptop. The laptop is one that should be around. So we don't need this. Okay. Hola. Siempre.
You sent, okay. Should be connected in Astro Edu. The link, where did you send me?
In the announcement, it was the
By email.
no, mandé el pero pensaba que importante que no, pero bueno, que con esto ahora conexionado todo esto revisar por el cuadro sí, por los que y ya con esto vale. Entonces debe que ahí sí, pero entonces ¿cómo es porque me dice que salía directamente de Windows, pero esta que se sabe que es la de sí, entonces hay que finalizar